Alright, welcome to Physics 2, Lab 5, Faraday's Law. Alright, so the purpose of this lab is going to be to study magnetic induction and eddy currents by analyzing observational data of a bar magnet falling through an aluminum tube and comparing real-life results to a simulation. So for the system, we're going to have the bar magnet and the aluminum tube, a tube of aluminum foil, and the surroundings will be everything else. For the computational model, we're going to be using glow script. The results are 0.24 seconds for experimental time and then 0.3 seconds for the computational time. Fundamental concepts needed for this lab are Faraday's law, which states that a changing magnetic field through a loop induces a voltage that is proportional to the derivative of the magnetic flux of that magnetic field, but in the opposite direction. The opposite direction part is part of Lenz's law. The Biot-Savart law, a steady current produces a magnetic field around it with the strength depending on the current and the distance from the current carrying segment. We also need Newton's laws of motion. So the second, it states that external force on a body is equal to the change of momentum in a system over time. And third, for every action, there is an equal and opposite reaction. So, some assumptions that we're going to make for this lab are that there will be negligible air resistance, that the bar magnet is sufficiently far from the metal, that the bar magnet will act as a magnetic dipole, and that the only forces that are acting in the system are the magnetic forces from the magnet and the gravitational force from the Earth. So, our experimental data, this is what we did in real life. We measured the length of the tube, the diameter of the inside of the tube, and the outer diameter of the tube, which are listed here. First I did it in inches, and then I calculated it to be in centimeters. Here are the magnetic properties we also measured. We calculated the magnetic dipole moment as well. Here are the time trials that we did. I did this by recording with my phone and then checking the timestamps for the time that it took for the magnet to fall all the way through. The average time that it fell was 0.24 seconds across all 5 trials. For the simulated data, on the left we have the input of the 2 properties that we measured, the magnet properties as well, and then we start to get into calculations. On the top we have the calculation of the dipole moment from lab 3, and then on the bottom we have the calculation of the flux, the magnetic flux passing through the area, which we measured on the tube, and using the magnet force that we just calculated, as I said, from lab 3. On the right here we see our simulation, the tube and the blue showing the north magnetic pole and the red showing the south magnetic pole, the graph of the velocity versus time on the right, and the final description of 0.3 seconds for the time that it took to fall all the way through the tube. Interpreting the simulations. So, which color corresponds to clockwise versus counterclockwise current? Via Lenz's law, the red is the counterclockwise current and the blue is the clockwise current. What happens if we flip the magnet? The magnet would fall the exact same as before, except the current would move in the opposite directions because the cross product considers the negative or positive and which way the current is being pushed, and the magnetic field is being pushed as well. How does observed time compare to simulated time? So computation is slightly longer, so errors in measurement and like the frames of the video, the frame rate of the video was actually slower, so you weren't able to tell exactly when it came out of the tube. You were only able to get as close as possible, like the single frame where you can see it out of the tube. You can see it no longer visible above the tube. What does the plot shape tell us about the forces acting on the magnet? So because we have this kind of pretty significant down curve towards 0, we can see that the magnetic force of the magnet in the tube was not strong enough to oppose the gravitational force of the Earth. Some errors in this video, in this lab, are measurements. The use of video is not as completely accurate because you can't get as close to it. You can't get as close to accurate as you would be in a simulation as the camera. Friction, the magnet hit the tube a couple times going down, and air resistance. All these would possibly slow down the magnet. What if the tube resistivity was close to 0, and how would the magnet dynamics change? From Ohm's law, decreasing the resistance would increase the induced current and producing a stronger opposing magnetic field and slowing down the magnet even more. What if slots were cut into the tube? There would be less current rings within the tube, and overall producing a weaker opposing magnetic field and causing the magnet to fall faster. Thank you.